In today's lecture, we're going to discuss time evolution in quantum systems. So up until now, we've discussed a lot about how to describe quantum systems, how we have operators acting on state vectors. They have eigenvalue equations for each operators. There's different bases we can look at. All of these are sort of how to describe the system in in our sort of quantum mechanical formalism. We talked about measurement, but we haven't really got to time evolution. How do quantum mechanical systems change with respect to time? In classical mechanics, one way we do this is we use Newton's laws, right? So you look at a system, some object, and we look at all the forces on it, and F equals ma is a differential equation, right? For the position of that object as a function of time, we solve that differential equation. We know that position as a function of time. We know the state of that object as time goes on. We haven't done that. We haven't figured that out or got to that part in quantum mechanics yet. What is the differential equation that's going to lead to our time dependence of our system? And what it is in quantum mechanics is we get this from postulate 6, where it says the time evolution of a quantum system is determined by the Hamiltonian operator through what is known as the Schrödinger equation shown here. IH bar, the derivative of the state vector with respect to time, is equal to the Hamiltonian operator acting on that time-dependent state vector. So the question then becomes, well, what is the Hamiltonian? And well, the answer is it's the energy operator. Now, if any of you have taken classical mechanics, either with me last semester or somewhere else, you might recall that in classical mechanics, the Hamiltonian was equal to just the total energy, the kinetic energy T plus the potential energy U. In quantum mechanics, it's the energy operator. It's the same sort of thing. It has an eigenvalue equation. So when it acts on one of its eigenkets, an energy eigenket, it returns En, the total energy of that state ket in the eigenket, times that energy eigenket. So just like the other operators, it has its eigenvalue equation, but the eigenvalues are the total energy of the system. Now, these eigenkets form a complete basis that are orthonormal, just like the other operators we've looked at. So we can expand any general state function in terms of that energy basis. So it looked like this, just a linear combination of all the energy eigenkets. So if we take that now and substitute that state vector into Schrödinger's equation, if you recall, it was just IH bar, the derivative of the state vector with respect to time, is equal to the Hamiltonian acting on that state vector. So if we write the state vector in terms of the energy bases and substitute that in, we get this. And if we go just do some math in there, that Hamiltonian operator can now be factored into that bracket and act on each of the eigenkets, giving just the energy of the eigenket times that eigenvector. And now we have this is another way of writing Schrödinger's equation. Now, one thing I want to say is we've assumed that the Hamiltonian is not time dependent here, right? So if you were doing something, or if the system was changing so that the potential energy of that system changed over time, or then those energy eigenstates would actually change as well. We're assuming a constant Hamiltonian here, so that those energy eigenkets are constants in time, and all the time dependence comes from the time dependence of the coefficients that make up that linear combination of the state vector. So anyway, short little aside there. But back to this, we've rewritten Schrödinger's equation in terms of our energy eigenbasis, right? And what we can do now is you can sort of see that the coefficients for each eigenket end up having to be equal on each side of this equation. One way you can see that explicitly is you take any eigenbra, we'll call it EK, the kth eigenbra, and bring that in from the left on both sides of the equation. If we do this, all of these constants can just come out to the other side of it, and we end up with EK, the inner product of that kth eigenket with each of the nth eigenkets. But since the energy eigenbasis is orthonormal, they're orthogonal, that these inner products here and here are going to be equal to 1 when k and n are equal, and 0 at all other times. So this equation simplifies to just IH bar, the derivative of that kth coefficient with respect to time is equal to that kth coefficient times the energy of the kth eigenstate. Right? So this is a differential equation we can solve, and if we've solved for those coefficients with respect to time, plug them back into our state vector, expanded in that energy basis, we have all the time dependence of our state vector. So now, how do we solve this differential equation? Well, the simplest way, I think, is separation of variables. We bring all the c terms to the left, all the time terms to the right, and you get this equation. You integrate that from t equals 0 to some later time t, and when we do that, we get, the derivative, or the integral of 1 over x with respect to x is the natural logarithm. This is just a constant, so we fire off the t. So we have ln, after we apply these limits, the coefficient at some time t and the coefficient at time t equals 0, we get the natural logarithms, or the natural log of the ratio of the two. We take both of those to the power of e and solve for our c, or our coefficient with respect to time. And we have that kth coefficient is equal to the initial coefficient, kth coefficient at time t equals 0, times this exponential with this phase factor dependent on the energy of that kth state. Right, so hopefully we followed this, and you're familiar with solving these differential equations from Math 346 or whatever math physics course you've taken in the past. We can now write that state vector as a function of time by just including this phase factor dependent on the energy of those states in our expansion in the energy basis. We at t equals 0, we just had that ck of 0. As time evolves, we get this additional phase factor for every on every coefficient in that expansion. Right, so the time dependence comes from that phase factor on all the coefficients in the energy basis. So let's see how this works. If we look at a system initially in one of those energy eigenstates. So at t equals 0, the state of the system is in the, we'll say, the nth energy eigenstate. As in that coefficient at t equals 0 equals 1. So the time-dependent state function is 1 times that energy-dependent phase factor, e to the negative I, the energy of the nth eigenstate over h bar times t, and that's the exact same state as it was at t equals 0, only different by a global phase. And we know that we've discussed several times that global phases are unphysical. They don't really matter. We can sort of set that global phase to be whatever we want, so we can just get rid of it. The state doesn't change with respect to time. These two states are equivalent, the psi of t or the psi of t equals 0. And this is why energy eigenstates are what we call stationary states. If the system's in an energy eigenstate, it stays in that state as the system evolves in time. Right? So let's look at a slightly more complicated example. Let's look at a superposition state, a system that starts in a superposition of two energy eigenkets. Pick any two of the eigenkets, the nth and the mth eigenkets, and some linear combination of those two, right? If I want to know the time-dependent state function, I just have to include those energy phase factors, where this one's dependent on the nth energy, the energy of the nth eigenket, and this one on the mth eigenket, right? Now, if this is the case, we can look at, well, what's the probability that I measure it in, if I make a measurement of the energy of this system, what's the probability that I measure this system in the nth eigenket? right? So at t equals 0, what's that probability? Well, we know from the postulate 4, the probability of measuring that eigenenergy is just going to be, what the measurement result was, that eigenbra, times what the state of the system was when we made the measurement, i.e. at t equals 0. So if we do that inner product, what we're going to see is it's just equal to Cn, right? If I do the inner product of this energy eigenbra, the nth eigenbra, with these two, well, the inner product of En and En is going to be 1 because they're orthonormal, and the inner product of En and Em will be 0 because they're orthogonal, so I'll just be left with this Cn coefficient, all squared. I get that probability. If I look at it at t equals t at some later time, I get actually, I do the same thing. I take that inner product of the nth eigenbra with this state function as a function of time. And again, this term is orthogonal to the E sub n bra, and this inner product goes to 1. So I'm going to be left with this whole coefficient, the magnitude of it squared, and the e to the I En over h bar times t terms will multiply to 1 when you multiply that with the complex conjugate. So I'm left with Cn squared as well. So again, the probability of measuring that nth eigenenergy does not change with time. Similarly, if we were to look for the probability of measuring the mth eigenenergy, we get the exact same thing. Neither of those probabilities change with time, right? So the probability of measuring the system in a given energy eigenstate is going to be time independent, is what we've just shown. But we need to be careful. We might naively sort of think that means, oh, well, then the state of the system isn't going to be changing. That is not true. The state of the system, that does not mean the state of the system is going to be time independent, right? To see this, we have to consider a different observable, not just the energy, but let's consider some other observable in this system, represented by operator A, right? A is going to have an eigenvalue equation like this. A operating on its eigenket is equal to the eigenvalue of that observable times that eigenket, like all our eigenvalue equations. Now, because the energy eigenstates form a complete basis, we can expand these eigenvectors rather of the A operator in terms of our energy basis. And again, it's just these vectors can be written as a linear combination of our energy bases. For simplicity, we don't need to assume this, but it's much easier to show in just the two-part in this example. Let's just assume, for clarity, that we're going to have this kth eigenvector for our operator A is just a superposition of the nth eigenenergy vector and the mth eigenenergy vector with some combination alpha n and alpha m of those two. And now we can ask the same question: what's the probability of measuring this observable in state AK, right? The kth eigenvalue of that observable A. Well, again, we're going to go to postulate 4 and look at that probability as a function of time. It's just the inner product of the observed eigenvector with the state of the system at the time we made the measurement, all squared. So, if we just plug in what we have for those two values, well, my eigenvector, as we showed on the last slide, is a linear combination of my eigenenergies. So the eigenbra is just going to be the complex conjugate of those coefficients times the energy eigenbras. And we showed previously that the state of the system as a function of time for this superposition state is the superposition of those two eigenenergy vectors with the phase factors in them. So now, because we know the energy eigenkets and bras or orthonormal, we can actually perform that these inner products, right? The En term here and the En term here are going to have an inner product of 1, so we get the two coefficients come through. This En and this Em are going to be orthogonal, so those just end up being 0. Likewise, Em and En orthogonal, so they're 0. Em and Em are normal, so that they're going to, the inner product of those are 1, and the Am complex conjugate and the Cm e to the I phase factor come through, and we're left with this as the probability of measuring the A sub n eigenvalue. If we carry this through, take a bunch of algebra, but you end up with this. These are equal. You have the An, Cn, magnitude of those squared, Am, Cm, magnitude of those squared, and then the real part of sort of the cross terms. Note these alpha n and Cn, it's actually the complex conjugate of this. So anyway, what we're seeing here is that there is a time dependence in the probability of this observable, whatever it is, and it has some time dependence here. This energy difference between the two energy eigenkets that the state was in divided by h bar actually is units of angular frequency, and we call that the Bohr frequency. We'll see why in an upcoming lecture. Hopefully you followed this. That the gist being, the general approach to how we're going to go and see how systems evolve in quantum mechanics is you're going to start with the Hamiltonian. That's going to be the time evolution, or the energy operator. And you're going to determine, you want to diagonalize it so we can have the eigenvalues and eigenvectors of our Hamiltonian, right? When we have that, we can write the initial state vector in terms of these energy eigenvectors rather, in this energy basis here. Once we have that, to get the system as a function of time, we just have to include these this extra phase factor that depends on the energy, the eigenvalue of each of these energy eigenkets. So this gives us our state vector as a function of time, and then once we've done that, we can look at the probability that we're interested in. What's the probability of measuring some observable at some later time? But basically, once we have this, we can look at our expectation values or our probabilities at whatever time we want, because we have our state vector as a function of time, how the system evolves in time. In the next video, we're going to look at a specific example of this for our spin 1/2 system, and hopefully that'll help kind of clarify this. Personally, I think things make a lot more sense to me after I've looked at a concrete example. This has been pretty general up till now. So next video, we'll get into a spin 1/2 system and spin precession.